Hi and welcome. I'm trying to learn electrical engineering, today thermoelectricity. And after we've done it, we're going to do wrist training. And if you participate in the wrist training, then it's better at your own risk. The fact that the heat produced by a current is directly proportional to the square of the current is sometimes known as Joule's law of heating, and like all laws in science, it is capable of experimental verification. So the heat produced is proportional to the square of the current. For this purpose, we need a calorimeter, polished and legged to minimize heat losses, and containing water. Into this water is placed a coil of resistance wire through which a current is passed. The size of this current is read from the ammeter, and the time for which it flows from a stop clock. The water will of course become warmer, and the temperature rise due to the passage of a current can be read from the thermometer shown. So we're having an ammeter or something leading electricity or current through a wire in the water, and up again there's a thermometer, whatever. And that measures the temperature. We're also storing the time, how long it takes, and also to measure how much electricity we bring through it. In this experiment, the volume of water in the calorimeter will always be the same, and different sizes of currents will be passed through the heating coil for equal lengths of time. So the volume of water is the same. Yes, we should really repeat the experiment with different volumes of water, but with different amounts of current, with equal time periods. It is an advantage to start each time from room temperature, so that heat losses will be much the same when each current is used to produce a temperature rise. The results obtained should be tabulated as shown. You will notice that the temperature rise should be known accurately, and to do this a sensitive thermometer marked in tenths of degrees is necessary. Okay, current ampere, we have 0.3, and the current squared, ampere squared is 0.09. And the temperature rise in degrees Celsius is 2.7. Now we're using 0.5 current ampere, and the current ampere squared is 0.25. And the temperature rise is 7.4. With current ampere of 0.7, we're having 14.8, and with almost 1, we're having 24 temperature rise. Do we say it is, you can make with a higher current easier water warm, unproportional, so exponential or whatever? Water, if you have, it is easier to make more warm with more water? Would be interesting. I don't know, maybe it's completely proportional, I don't know. Once again, we can plot our results graphically to see whether a straight line through the original results. If so, the experiment will have verified that the quality of heat produced by current is directly proportional to the square of the current. Our next task is to consider the effect of resistors connected in series and parallel in terms of the quantities of heat produced in them. For this purpose, you will need two lengths. Is it something else? Is it nothing to do with water? Now, as I see it, if you double the current ampere or triple it from 0.3 to 0.9, you have not a temperature rise of 3, but 24, which is 8 times, not 3 times as much. Okay, next task. Our next task is to consider the effect of resistors connected in series and parallel in terms of the quantities of heat produced in them. Now, the thing is, we didn't really understood the resistor thing with connected in series and parallel. It was sometime at the beginning. For this purpose, you will need two lengths of wire, each about 9 inches long, one of copper, 30 standard weight gold or what it was, and one of nichrome or constantan of the same gauge. It's convenient to pin these down on an old wooden board so that no damage is done when the wires become hot. First of all, connect these two wires in series and apply a potential difference of about 6 volts to the ends as shown for only as long as it takes to observe which wire becomes red hot first. The copper of low resistance or the nichrome of higher resistance. In fact, you will find that the higher resistor becomes hot while the lower resistor is only warm. Okay, the higher resistance in the wire or cable we bringing the electricity through, the hotter it gets. So more resistance makes it hotter. It has happened in some apparatuses somewhere that things getting hot because they are not properly leading the current. In fact, you will find that the higher resistor becomes hot while the lower resistor is only warm. By altering the current leads to the two wires, it is easy to apply a potential difference to them connected in parallel. This time you should find that the copper wire of lower resistance becomes hotter than the nichrome wire of higher resistance. Why? What do we mean in parallel? These results may be surprising. In any case, they certainly need detailed explanation. Or detailed explanation. Consider first the series arrangement. Oh, we had in series. The first one was in series. 2 lengths of wire. To connect these 2 wires in series. And then we had them in parallel. When we had them in series, the higher resistance part got hotter, and we had them parallel, so not the same current going through the same one, when the lower one got hotter. So, the explanation. Consider first the series arrangement. The current must be the same in each wire as the current has to flow through each in turn. So it is in series, first here and then through back. We now need to use 2 mathematical equations which were explained earlier. Power equals VI watts and volt equals whatever I times R. These relationships are both true for any circuit at any instance of time. So that such a pair of equations are referred to as simultaneous equations. The second equation can be used to replace V in the first equation, a process of substitution, so that we have power equals I squared R watts. Now the rate of energy conversion in our 2 wires from electrical energy to heat energy is power. The more energy which is converted per second, the greater the power consumption in the wire. When our 2 wires were connected in series, the same current had to flow through each in turn, so the power or rate of heat production in the 2 wires depended only on the resistance of each. The higher resistance of a constantan or nichrome wire caused it to produce more heat than the piece of copper wire with a much lower resistance. The rate of energy conversion in our 2 wires from electrical energy to heat energy is power. The more energy which is converted per second, the greater the power consumption. And the power consumption is greater when there is more resistance. So there is more conversion of electrical energy into heat energy, and therefore the resistance one gets a high temperature. Now to consider the same 2 wires when arranged in parallel. Then you will remember the copper wire became the hotter of the 2, so the one with less resistance. Once again, we use our 2 equations. Power equals VI watts, V equals IR. The second equation can be rearranged to read I equals V divided by R, and this value can be substituted into the first equation so that we have a result power equals V squared divided by R watts. Because the 2 wires are joined at both ends, the potential difference across each wire must be the same. So we have 2 situations. Power used to produce heat in copper wire is V squared divided by lower resistance of wire, and power used to produce heat in nichrome wire is V squared divided by high resistance of wire. And as we know from our experimental evidence, the left-hand expression is greater because the denominator is smaller And it is the low resistance copper wire which becomes the hotter of the two. So now we have seen that we can calculate the power used to produce heat in any resistor by using three different equations. Power in watts equals I squared R, or V squared divided by R, or V times I. Where I is the current in amperes, V is the potential difference in volts, and R is the resistance in ohms. Heat is, however, usually measured in calories, a calorie being a unit of heat energy. Mechanical energy is measured in joules. A rate of working of 1 joule per second is indeed what is meant by the term watt. It is found by careful experiment that when mechanical energy is converted into heat energy, 4.2 joules of a former produce 1 calorie of the latter. Okay, we don't have time to push this on. Because the two wires are joined at both ends. Why are they joined at both ends? We should make them parallel. Why should they be joined at the end? The potential difference across each wire must be the same. So we have two situations. Why are they joined? Okay. As I said previously, we don't really understand it, but we can follow. It was the electrical engineering part. If you were here for electrical engineering, you can go to an expert of electrical engineering. We're going to talk on about electrical engineering. On that point, we already done. If you stay here and participate in the wrist training benefit, the always go to step and stance, hands to fists next to the body, bring them down and up. The spotlight. And in the flashlight. And hands flat, and the magician. We're having three rules. The first rule is with stopping immediately as soon as there's pain. Flat hands and open and close. The pancake flipper. The second rule is that we're going only as fast as we can go with a little bit of effort. The T-Rex in the morning, hands down and up. And the third rule is that we're not overdoing it. Just want to strengthen, not to exhaust. And we could then go to cast like fists in, up, out, down, in, back, down, up, in. And arms up, down with fists into flexion, down with the arms. Again up, turn it around, again down, fists in flexion all the time. Turn around, down. Hand next to the body, down, into flexion, press on the outside. Press from the outside, the inside. And from the top. The crab anxious to have fever. Crab anxious to have fever is the extent. Outside. From the outside. Top. And now, coarse sweeping, fingertips of one hand on top of fingernails of the other hand, open claw. And with the other hand, switch. And now the T-Rex in the gym, you can do it with a tennis ball, press out of a tennis ball, or just make a strong fist, release, press again, release, press, switch, press, release, press, release, press. And now the field is in the synthesis director, fists open, close, open, spread the fingers. In the bicycle bridge, flat hands, bend the fingers at the knuckles, open, close, open. With rock testing the water temperature, down with flat fingers. You can take a break whenever you want. Up the fists, down the third rule. You just want to strengthen, not to exhaust. Up. And now hands and make closed, flare the fingers. Up, close, and close. And arms in, strong fists into flexion, out, extend. In, strong fists, flexion, out, extension. One more round, out, extension, in, flexion. And the eyes extended hand, press onto all four fingers. Other hand. And the rocket boosters launch, or boosting rocket, long arms, strong fists into flexion. Out extension. The rocket boosters launcher. And again out. In. One more round. In. And the claw go with moderate pressure over the middle part of the lower arm. On the other side. And that was the wrist training. I thank you very much, and until next time.